Okay, so I want to continue with the definitions that we were playing with yesterday, and then do lots of examples. So, we said M is a k-dimensional manifold with boundary. If for every p there is a neighborhood that is the image of a parameterization G so my M is sitting inside some Euclidean space. I forgot to say that yesterday. So I've got.
I don't think we did this yesterday.
Yes, we did. Where U is open in either RK or RK plus. So remember RK plus was the upper half plane, so it's the points whose kth coordinate is greater than or equal to 0.
So Sk is the kth component of vector x?
Yeah. Yeah. So if you have a manifold that looks like this, and then it has, say, these edges that are like, so I'm imagining that you're walking along the surface, and when you get over here, if you keep walking, you fall off, you fly off into space. Or if you walk here, you fall into a black hole, and you fall off into space. So these would be the boundary piece. So any x, any p, that is the image, so it's G of some U with UK equal to 0. So if you have some parameterization that's working from a piece of RK plus, and you've got a point that's coming from the boundary of RK plus, namely a point where the kth coordinate is 0, then such a point P is called a boundary point. So it's like the frontier, but it's called boundary. And the set of boundary points is written for reasons that don't entirely make sense. Partial derivative of M, that's read boundary M, is the set of all P that are boundary points. So basically, there's two types of points in your manifold with boundary. There's points that we're used to that have neighborhoods that look like you can move in all directions with k degrees of freedom. And then there's points that are on the edge, boundary points, where you can move in most directions with k degrees of freedom, but you can only move in this direction inward, you can't move outward.
Like k minus a half?
Well, not exactly, but I get your point. We're still, all right, so, and the parameterization obeys all the rules that we had back in our definitions. This is supposed to be a one-to-one map. The derivative is supposed to have rank k. All the technical things we had back in chapter 6 are still in play. Okay. So I want to just talk a little bit about orientation. I don't want to make a huge deal out of this, but I want to talk about it a little bit, and then we're going to do examples. Stokes theorem, actually. Okay, so an orientation, just as we were discussing for surfaces yesterday, an orientation on this manifold M, or manifold boundary, is a continuously varying assignment of an orientation to all the tangent spaces TPM. So you're going to ask me, well, what is an orientation on a vector space, on a tangent space? So an orientation on RK is basically an assignment of,
It's about to be away. I just can't. I promise.
it's an assignment to each ordered basis for the vector space of either a plus or a minus. So you take all your bases and you sort them into two categories: the good, the bad, and the evil. No, wait a minute. I guess there's three categories. No, there's only two. So an orientation on RK is a choice of plus or minus for each ordered basis. And two ordered bases will give you the same orientation if the linear map that takes one to the other has positive determinant. So if V1 to VK and V1 prime to VK prime are two ordered bases,
Are there always only two possible oriented?
yeah, you'll see why. If there are two ordered bases, they define the same orientation if and only if the matrix that tells you, this is a K by K matrix, that tells you how to get from one basis to the other has positive determinant. So I write down Vi prime is summation A, no, let's say Vj prime, A, I, J, V, I. As positive determinant. So rather than trying to make, so to answer Ken's question, if you have two ordered bases, you have a non-singular matrix that tells you how to get from one to the other. Each can be written as a linear combination of the other. That has to be a non-singular matrix because you can go backwards and solve for the v's in terms of v prime, so it has to be an invertible matrix. If you have an invertible matrix, its determinant is either invertible is equivalent to what about determinant?
Not zero.
Not zero, so it's either,
Positive or negative.
so there's your two. So take any two bases, you fix one of them and say, okay, I'm using you to measure everybody else, call him positive. Take any other basis and you test out, do I get a positive determinant when I change from one basis to the other, or do I get a negative determinant? Those are my two sets. So for example, if I took the standard basis for R2, and I took this basis, then, for example, if this were if these were the standard basis vectors, and this were the vector, say, 2, 2, and this was the vector 2, negative 1, I would write down the matrix whose column vectors were these vectors, and I would have this matrix, and I would ask myself, what's the determinant? Which I believe is negative, so that means these define opposite orientations in R2, which is consistent with what we've been saying all along. Okay? So this makes sense when you can't think right-hand rule in k dimensions. This is how you officially define orientation.
It's generally right-handed, the positive one.
Yeah, yeah. So ordinarily, we talk about the standard orientation on RK given by the standard basis and call that a positive orientation. And then what you're going to do is you're going to transport from your parameterization, you're going to transport orientations on RK to orientations on your tangent spaces by saying my parameterizations are going to be consistently assigning the same orientations everywhere on the image of the parameterization. Okay, so here comes the fun part. And this, you're not going to see for a few days why this is important, but this is important. Given an orientation on M, there is an induced orientation on the boundary points. So the boundary of M, which is itself a k-1 dimensional manifold. I haven't stopped to prove that. But if you know how to orient M, here's how you orient the boundary. So here's the picture. Here's M. And here's the boundary of M. At each boundary point, you say, okay, I'm going to take a basis for the tangent space of the boundary. I'll have k-1 vectors in the tangent space of the boundary. And I'll say they define a positive basis for the tangent space of the boundary. By definition, I need to relate it to a basis for M, for the tangent space to M. So what am I missing from these guys in the boundary? What do I need to get a basis for the tangent space of M? I need one more vector. And what the obvious vector to pick is an outward pointing normal vector. So I mean the normal to the boundary in the tangent space of M. So the picture looks like this. Here's the tangent space of M. Here's the tangent space of the boundary. And so in this k-dimensional space, I can take the normal vector that points perpendicular to the tangent space to the boundary, and that points out. What do I mean by out? Well, what I mean is in would be towards stuff in the manifold. So this n points away from the manifold. That's what outward pointing means. So with n, the outward pointing normal put the normal at the front. This seems weird, but you're going to see why it's important in a few days. You stick your vectors from your tangent space to the boundary, you put the normal vector first, And this should be a positive basis for the tangent space of M. Okay, so this seems very abstract. Let's do some examples. So this is going to tell me how I, given an orientation on my big manifold, how I get an orientation on the boundary. And this is what's going to make Stokes Theorem work. This is why I'm going through this fuss. Okay? So let's do examples. Let's take the upper half plane in R2, R2 plus. So here's R2 plus. And what I want to know is, the boundary is just a copy of what?
Yeah, exactly.
So it's just R1, right? So let's agree that we're taking the standard orientation on R2. So we're going to use the standard orientation on R2. How do I orient the boundary? Do I go this way or do I go that way?
That
Have you stopped and thought?
one. I'm just thinking that's standard. I thought it was not the one.
Well, why am I asking the question? It isn't always going to be standard. So, Ken, you said this way. So you're saying Cameron's right. Why is that? What am I supposed to do?
N is pointing down,
Okay, n's pointing down.
and we want that to be the.
I want right-handed.
Clockwise and down.
So I want minus E2, and then I want to say, is E1 going next, or is it minus E1? Well, minus E2, E1 gives you the same sign as I can, if I have minus, it changes orientation. Because if I take one vector and make it negative, that puts a matrix that has a -1. So what's the matrix here that compares this to the standard basis?
0, negative, going, oh, 0, negative 1, 1, 0.
Okay. And that has positive determinant. So in other words, putting it back in the standard form, I have a matrix that has positive determinant. And that agrees with the picture here that if you put minus E2 and then E1, that's a right-handed basis. All right. This is why I snapped Cameron. Do R3 plus. So you have upper half 3 space. The boundary is now a copy of
R2.
R2. Oops, we don't know what that sign means. Sorry. All right, standard orientation on R3. So standard orientation on R3 would be the standard basis. E1, E2, E3. N pointing down.
So no, negative E3 is in the first.
Negative E3 is first.
So now we just have E1, E2 to worry about. And we'll make a positive determinant.
Right. So is this ordered basis equivalent to the standard basis or not? So if I put E1 and then E2 after negative E3, is that a positive basis for R3 or not?
No, that's negative.
It's negative. So this is negative the standard basis. So what do I have to do?
Add negative to either E1 or E2.
Or switch the order. Either way. Either make one of them negative or switch the order.
But why is E3 negative?
Because outward pointing normal means I'm going down away from
Okay.
the upper half space. So E2 is going to come first, E1 is going to come second. Oops, I drew that wrong. I drew negative E1. So we're going to do E2 first, and then E1 second, and that would make a positive basis with respect to this boundary orientation. So what do we conclude? We conclude that the boundary of RK plus is RK minus 1, but not always with the right orientation that we're used to. It's a plus or minus, and what's the sign? It agrees when K is even, and it disagrees when K is odd.
So this is just K.
Yeah. So by this I mean, when K is even, the orientation on the boundary is the standard one, and when K is odd, it's the opposite of the standard. Okay? So this means the boundary orientation is plus or minus the standard orientation on RK minus 1, plus when K is even, minus when K is odd. Okay? Guess what? This is where my crazy walk with the region on your left came from. Remember when we talked about Green's theorem? We said the way you orient the boundary curves is you make sure that as you walk, that the region is to your left. That's consistent with this. Suppose this is your oriented surface with boundary. So this is M. It's a two-dimensional manifold with boundary. What's the boundary orientation? Okay, so I've just said that at a boundary point, you have to take the outward normal and then the correct direction so that that gives you the correct orientation.
Out of board.
So that means you're going to walk this direction on the boundary. This should also remind you of homework problem 17 in section 3, where you remember N and T is supposed to make a positive basis when we're doing a curve in the plane. Well, that's what this is. Okay, so this is where I said you walk in the direction so that your left arm is pointing into the region. The outward normal is your right arm. Okay, and then consistently then, when you get to this piece, the normal is pointing outward, means to the inside there, and then T has to go which way? Well, I still have to have a right-handed system, so T points that way. So the walk with the region on your left rule is absolutely consistent with this. But this tells you what to do in higher dimensions when I haven't told you what the generalization of this is. Okay?
Why did they decide that M would come first?
Because this gives the correct sign to make Stokes Theorem work, as you're going to see. And if I put N at the last, then I have to count. It depends on what K is. So I want to get this sign to make Stokes Theorem work. And if I put N at the back, then I have to have a minus 1 to the K something. That's why. So it was just discovered that that makes the easiest definition. All right, so here's the statement of Stokes Theorem, and we're going to spend today and tomorrow doing lots of examples before I worry about proving anything. So I put it up in very sloppy form on the board yesterday. I'm going to actually try to state it correctly today. But you can never be sure that what I say is correct. All right, theorem. Stokes.
Stokes is.
No, this is the person whose theorem it is.
Okay.
No apostrophe. The history of this theorem is rather complicated. I mean, we've already seen Green's theorem as a special case. The Russians have a few people that have names on it. The Stokes actually was working on physical type stuff, actually trying to understand fluid mechanics when he came up with this. The ultimate version in terms of differential forms and manifolds in higher dimensions came after Mr. Stokes. That was not his doing. That came along quite a while later. But it still gets his name on it everywhere except in Russia.
Oh, when was he around?
Mid-1800s, I believe. The differential forms came later. So the theorem is this. Let M be a compact, oriented, okay, so I've provided an orientation, k-dimensional manifold with boundary. Let omega be any smooth k-1 form on M. So it has to be smooth on all of M. That's important. Then, integrating omega, well, I can't integrate omega on M because it's only a k-1 form. However, we have conveniently the boundary of M, which is a k-1 manifold. So I can integrate omega on it. Now, I haven't told you officially how to define how you integrate forms on manifolds in high dimensions. I will. I will actually talk about that eventually. But you need to have an orientation to make sense of it. Because all the stuff we've done, we've talked about parameterizing and making sure that your order is compatible with the parameterization. So you need to have an orientation to make sense of this. But we will talk about that more. I've told you how to have an orientation. That's what all this was about. So then integrating omega on the boundary is the same as integrating d omega on M. And here, boundary M is provided with the boundary orientation that we just finished discussing. Now there is a plausible question to ask, and you can either ask it now or ask it later. So what's the question?
What's the question?
Right.
That is the question.
I'm waiting for you to ask me the question.
I don't know if this is the question you wanted, but if the boundary of M has a different orientation from what you would get, right? Like, because you have the orientation of M, and then you have the orientation of boundary M.
Well, but I'm saying following these rules, having an orientation here provides you canonically with an orientation there.
Okay.
So that wasn't the question.
We only know that W is smooth on k-1 form on M, so we don't know if it's smooth, DW smooth on a...
No, if omega is smooth, then d omega is smooth too. Right, all the coefficients are smooth functions. Then you take d, you're going to get everything. So no one wants to guess what the question is? So, suppose M were not a manifold with boundary, but a manifold by itself that was compact.
Oh, how would you integrate with
What are you saying? Yeah.
Suppose M is by itself, M is by itself a compact k-dimensional manifold. So what do I mean by that?
Like a closed surface of sphere.
Right, that's exactly right, Ken. Like a sphere. So what's the boundary of such a thing?
There is no boundary.
There is no boundary. So boundary M is the empty set. What in the world does this theorem mean then?
Equals 0.
Does what have to be 0?
omega over an empty set sounds like it's zero.
Okay.
Therefore, dw over n sounds like
Right, and that's what Stokes Theorem says. So in the event that m has no boundary, as Lama correctly surmises, this is zero. So we get the result that integrating an exact K form over a manifold whose boundary is empty is zero.
Makes sense from flux perspective.
Well, we'll see how that works later. Okay, I mean it's a little subtle to see that, but here's an alternative argument. If this makes you squeamish, is this making you squeamish that Lama's saying this should be zero because there's nothing to integrate over? Does that bother you?
No.
No.
Well,
Is there anybody that bothers who will confess to it's bothering them?
is that only when omega is exact?
Yes.
Okay,
I mean this only applies to d omega here, right?
that doesn't bother me then.
Okay.
I was worrying about how you would integrate the boundary, but the boundary's not exact. Or
It
the
doesn't,
boundary is
empty set doesn't really have orientation.
Right, but there's nothing to integrate over. Alright, so we'll pretend Ken's squeamish.
Come on, Ken.
So here's your compact manifold that has no boundary. And I want to give you an alternative argument for why this should be zero. Okay, I mean you're gonna complain that I'm hand waving some stuff here, but this gives you the right intuition and this shows up in a lot of physics arguments as well. So I think this may be actually what Cameron was sort of thinking about. Imagine that you come along somehow and you saw M into two pieces. I don't mean past tense of C, I mean saw M into two pieces. So I'm going to write M as M1 union M2. So I come along and I cut it up somehow, and I have the right-hand piece of M and the left-hand piece of M. So here's M1 over here, and here's M2 over here. They now each have boundary. Because when I took my saw and cut through M, I created a boundary. You see where we're headed?
Yeah.
So here,
But then induced boundaries go in the
Boundary,
opposite
yeah.
direction.
there you go.
Gives you orientation.
So the boundary of M1 and the boundary of M2 are the same set,
But with opposite orientation.
but the orientations are opposite.
Fit together, they
Say again? Oh, no, but I'm not talking about the orientations on M1 and M2. I'm talking about the orientation on this piece here.
How are they opposite? Why?
Because the outward pointing normal, when you're living in M1, clearly points into M2. But the outward pointing normal when you're in M2 clearly points out of M2, which means it points that way. Right? So N is opposite in the two cases. So that flips the orientations. So do you see how the proof goes now? So integrating d omega over M is integrating over M1 plus integrating over M2, because I just sawed M into the two pieces. But by Stokes Theorem, this is the integral over the boundary of M1 of omega. This is the integral over the boundary of M2 of omega. So what did we just say? We said these are the same manifold, but they have opposite orientations. So what happens when you do the integral? It switches. So this is just like saying when you go backwards on a curve, the work is the negative. This is the generalization of that. If you orient oppositely, your integral changes sign. Okay. So you ready for examples? In hindsight, this is going to make a lot of your homework that you struggled with in past WebWorks perhaps easier.
Yeah, come on.
Homework on Induced web works much harder.
I don't think the homework you're currently struggling with has helped. All right, so we're going to do examples. So I'm going to make up one here that ought to remind you of some stuff we've done, but we'll see. So let's say omega is x. Let's see, what did I actually have here? Not that it really matters. X plus z dx plus y plus z, whoops, y plus x dy plus z plus y dz. So this is a one form on all of R3. No problem. But in R3, I want to imagine that I want to integrate it over a curve C, where C is the intersection of the cylinder x squared plus y squared equals 1, and did I actually put anything in my notes? I probably didn't. No, I didn't, so I'll just make something up. And the plane x minus y minus 2z equals now, so what's the picture? Here we are in R3. I've got myself a cylinder, and I've got myself schematically drawn a plane. Plane that goes through the arc, as it turns out. So again, I'm not going to draw it to scale, but I've got some plane. So what does the intersection look like?
In XY plane, it's X.
It's in this tilted plane, and it is an ellipse. So you've seen such things before. Now, why is this problem unsolvable as it stands?
Orientation.
I have not told you how it's oriented, so there's no answer.
There's only plus or minus.
There's only plus or minus an answer. So if you get a web work problem like this or an exam problem like this, you could say, well, the answer is plus or minus something, but web work wouldn't take that. So you should complain that it's not a well-posed problem. So I have to add oriented. So I have to tell you how I want to orient this curve, and I'll say oriented clockwise as viewed from high above. Now what does high above mean? I mean go way out the z-axis and look down. So above I mean relative to x, y, z. So your eye is up here. You're looking down, and you see that you're going around the curve clockwise.
We know what above is, but we have to define outward every time.
Well, I mean, is that outward?
Maybe that's what it is.
No, I mean outward, I could say always pointing with positive z coordinate, but that doesn't work when I'm on a cylinder, for example. I mean, when I'm saying high above, I mean relative to the z-axis, meaning for Ken.
This would be negative orientation of what we typically have.
Right. Okay, how am I going to do this? Well, this is not unlike problems you've been doing. It feels Green's theorem-ish. Why am I doing it now? Why am I invoking Stokes theorem rather than invoking Green's theorem? Well, Green's theorem we set up specifically applied in the xy plane. So you could parameterize everything and pull back to the xy plane, and we said yesterday that you would still have Green's theorem. But why bother? I can now say, oh, this curve surely is the boundary of some convenient two-dimensional manifold with boundary. What might the M be that would be convenient?
This.
No,
Elliptical disk?
elliptical disk. So you could say, let M be the region bounded by this ellipse in the plane. Let M be the elliptical region bounded by C in the plane. Now, of course, there are lots of other surfaces. I could make some sort of parabolic glove that fit that as its boundary curve. And I could make some sort of fancy bullet-shaped region. I could make up all sorts of M's, but why not use the most convenient one? But now again, to apply Stokes' theorem, I have to orient M. So how do I orient M?
Outward,
What does outward mean?
away from the red region? And
No, 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 no. M is this region in the plane.
So it would be,
How am I orienting this two-dimensional surface with boundary? So this is like doing surface integrals that we've been doing.
Just like the red on the left.
No, 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 no. You guys are worrying about how I orient the curve. Well, okay, okay. I mean, knowing how I want the curve oriented. Okay, maybe you guys were trying to do the right thing and I was being stupid. So you're saying, here I am with the curve. I want to go this way. So I want that to be my positive basis for the tangent line to the curve.
you want that to be, like, if you're walking on that, you want that being in the left, and you'd be standing upright.
So outward normal is pointing this way. Is it? So this is confusing now.
Well, you're walking around and it's on your right, so the outward, so it'd be pointing inward.
So, okay.
Not going from below.
Hang on.
But
So
we're not looking from below.
in this plane, you want me to draw,
The normal pointing in towards the center.
Or it's just orthogonals to the tangent.
no, I can't. This definition doesn't give me a choice of where n points. It has to point out of M perpendicular to the boundary.
It's easy.
So I have no choice but to put the outward normal to this curve pointing, I'm going to put this at a different point so it's clearer. I'm going to put the outward normal there, and we're putting that's how we've oriented that. So that means that the orientation on the plane has to be with this being a positive basis. This has to be a positive basis.
So the last vector has to point downwards.
So what's the orientation on the plane? It's
Downwards.
right. So if you wanted to talk about the unit normal to the plane, which we were also calling n for weeks, so this is really confusing. This n is normal to the curve in the manifold, but the plane has the opposite orientation. In other words, the plane's oriented with its normal in R3 pointing down. So this is the n for the plane in R3. So this is a little confusing because of the fact there's two n's in play. I apologize. All right, so let's finish the problem. I'm supposed to do Stokes' theorem. So I have an omega. I have an oriented surface with boundary. So I'm supposed to integrate omega over the boundary. Did I write down omega there?
Yeah.
Yes, I did. So I'm supposed to say the integral of omega over c, which is the boundary of m, is supposed to be the integral of d omega over m. So what's d omega?
1 dz dx. Just 1
1
I-
dx dy. dx dy.
Yeah, switch.
dy dc.
All right, how do you want to do this?
So why can't we use Green's theorem on move 4?
Because officially Green's theorem was in the standard R2. This is in R3, right? I mean, Green's theorem doesn't know what this means.
What were we doing on the last homework assignment?
You would have to parameterize and pull back, and then you could, then we are using Green's theorem.
Okay, but we're not parameterizing.
But I'm not gonna do it that way.
But we could.
You could. You won't be able to do it for the next problems we do, probably, but at least what I do tomorrow, we won't. All right, how do I finish the problem? Pretend this is a problem you've been doing in recent homework. How you've been doing surface integrals like this. You could do pullback, but there's an easier way. So you could parameterize and pull back. Or, what could you do?
It's, the thing with the integral is just the area. Integral one.
Related to that,
Is it average value?
well,
You guys just forward.
you're skipping steps. What's our alternative interpretation of, for a surface in R3, what's our alternative interpretation of integrating a two-form? It's a four-letter word.
Area.
Flux.
Flux. Think of this as a flux two-form. So my advice is if you have 12 hours to do a problem, feel free to do it the most complicated possible way. But hypothetically, if you're on a test and you have a large number of problems to do, you want to think about what's the most efficient way to get to the answer, not necessarily the way you're always going to think of first. What's the most efficient? Think of this as the flux of what vector field? Well, it turns out it doesn't matter what order they're in because it's all ones. But remember, the first one is supposed to be this guy, and the second one is this, and the third one is this. But in this case, it's immaterial because it's all symmetric. So how can I, without any huge mess, find the flux of that vector field across this surface M?
F dot n.
So, what is the normal? 1. And notice it has a negative z coordinate, which is pointing down, which is correct. Remember, I tripped you up on this last time, where we had to think about the sign, but this time I want a down pointing normal because of the orientation. So I want,
Because it ran clockwise?
yeah, and that made us have the normal to the plane pointing down. That was where we got with that picture. So F is 1, 1, 1. N, Patrick says, is 1 over square root of 6. 1, negative 1, negative 2. Is that right? So what do I get? I get negative 2 over root 6 times the area of the region. Agreed? This is a constant, which I believe I got correct. What's the area of the region? Area of the projection times 1 over cosine. So what's that going to be?
You got the normal with the E3.
What do I get?
Or do you, wait, so when you're done,
You really have an absolute value there, although I didn't make a fuss about that the other
Yeah.
day, right?
For this, are you doing the normal vector with negative E3, or does it even matter?
It does matter, and that's why we discussed all this.
Yeah, so do you do like this? So yes or no on the negative E3? No, not negative E3.
This is the correct normal vector because we said,
That's the correct normal vector, so you're dotting that with E3 or with negative E3?
it doesn't matter, I'm going to take absolute value here.
Okay.
The fudge vector has to be the absolute value. But the net answer is negative. All right, just to point out that you have a somewhat easier way to do that, an earlier problem. Suppose C were the curve obtained by intersecting the plane, the same plane, with the unit sphere. And we'll say oriented, just to be different, we'll say oriented counterclockwise. Dot, dot, dot. So does this remind you of a problem that you had in homework?
Yeah.
Which problem was it?
You would parameterize.
Right. So now you're getting a great circle in the sphere. And you had a homework problem a couple weeks ago to find an orthonormal basis for R3 where the normal vector was in perpendicular to the plane, and then you parameterized the circle and you did it, right? What's easier now?
Flux.
Do the same exact thing. Fill in the circle and do the flux across the filled in disk. So now let M be the disk. Filling in C in the plane. And you see how much easier this is. I still have d omega. I have a different surface. Instead of an ellipse in the plane, I now have a circle filled in. So I'm still getting the flux of the same f, but now have a different normal, because I have a different surface. But f dot n is still, well now I have to be careful, because now I said counterclockwise. So now I need n that points up. So I'm going to take the negative of the n, and f dot n is now going to be plus 2 over root 6. And now I'm going to get the area of the filled-in circle, which is pi. It's a unit circle in a plane.
Does it counterclockwise depend on like which way you're looking at it?
Right, but I'm saying the same discussion is there. So now I'm looking from high above, but now the area is just pi, because I don't have to do any projections here. It's just a unit circle, unit disk. So that's way easier than the hour you spent on the Weber problem where you had to find an orthonormal basis, parameterize the circle, pull back. Okay. So tomorrow we're going to go on and do 3- and 4-dimensional examples.